Hi, I'm Dan Bauer and welcome to CBA Office Hours. This is an online forum where Patrick Kern and I talk about statistical techniques and issues that arise in behavioral health and social sciences. Today I'm going to extend our series on the linear regression model. In past episodes I've talked about what is the linear regression model, what are we trying to do with the linear regression model, what are the parameters and their interpretation, how do we obtain sample estimates, and in the last episode we began talking about inference, and we talked about the overall model F-test. That is a way of evaluating, is your model predicting variance in your outcome above and beyond what you might expect by chance alone. Today we're going to talk about the t-tests that we obtain for each of the individual regression coefficients, as well as the confidence intervals that we obtain for our regression coefficients, and how we can use those to make inferences to the population. So our population regression model, right, just to remind you, is that y is equal to beta naught plus beta 1x plus some residual. In our sample, we estimate beta naught, so we get b0. We estimate beta 1, we get b1. And so we have sample estimates, b0 and b1, for those population parameters. All right, so we've got population and we've got the sample. And what we would like to be able to do is take our estimates of b0 and b1 and make inferences about what beta naught and beta 1 might be in the population. So to take our example from before, we might be looking at the relationship between performance as y and experience as x, and we might expect some positive relationship, right? Maybe I've sampled YouTube channels and I see how many videos they already have posted, and then for their latest video, how many views do they get as my measure of performance, and I might expect to see some kind of positive relationship, although I don't think that necessarily holds for our channel in particular, but maybe I see some kind of positive relationship there that shows that as number of videos experienced with doing this increases, then number of views increases as well. Right? And so this is my b0 plus b1x regression line that I estimate in my sample, but what if I got a weird sample, right? I only sampled maybe 20 YouTube channels. What if I'd sampled 20 other YouTube channels? You know, maybe what I'm seeing here is just, luck of the draw that I got an odd sample that showed a positive relationship when in fact there's really no relationship whatsoever in the population. So I want to be able to say, how much information do my estimates b0 and b1 provide me about the possible values of beta naught and beta 1? And we can use t-tests as one way of getting at this question, and we can use confidence intervals as another. But let's start out with the t-test. Okay. So like any other t-test, we begin by positing a null hypothesis. And so our null hypothesis is going to be, I'm going to focus on our slope parameter because we're typically more interested in that than the intercept, but the same logic holds for any regression coefficient you might be interested in. So our null hypothesis will be that beta 1 is equal to 0, that there is no effect of experience on performance. Right? And then our alternative hypothesis is that beta 1 is not equal to 0. Now you can also posit directional alternative hypotheses, but that's less common. Typically people would simply do a non-zero alternative hypothesis. Now we obtain our estimate. So we obtain our estimate of b1, and let's say our estimate is 2. Is too big or is too small? All right, so that would indicate that per additional YouTube video on the channel, the newest video has would be expected to have 2 more views or 2 more likes or something like that. Right? And so that would be our B1 estimate. Is that large enough to conclude that in fact this null hypothesis must be wrong in favor of the alternative hypothesis that we prefer, or is that within sampling variability of 0? Meaning in any given sample, even if beta 1 is 0, we're not going to get exactly 0, right? In any given sample we're going to get a B estimate that's slightly different from 0. And maybe 2 is within that slightly different interval. So we need to be able to establish whether 2 is large and implausible if the null hypothesis is true, or whether 2 is small and is plausible if the null hypothesis is true. If it's implausible, we'll reject the null hypothesis in favor of the alternative. If it's plausible, then we simply cannot reject the null hypothesis. All right, so what we need to know then is if beta 1 is actually 0, then what is the distribution of B1 values we would expect to observe were we to draw samples from the population? All right, and so beta 1 is in fact 0, right? That's our null hypothesis. We're going to pretend that's true. And then we draw samples, and each sample we get a different B1. If we collected all those B1s together, we would get something that would look kind of like a normal curve, right? That would be our distribution of B1 values. So now, given this sampling distribution, I can say, all right, given that sampling distribution, how extreme is a value of 2? If that value of 2 has very low probability, then I would say beta 1 probably isn't in fact 0. It's implausible for that to be the case. In practice, right, we look at both tails of the distribution, so we look at 2 as well as negative 2, and we say how likely is it I would get a B1 value as extreme as 2 or negative 2. So that's typically what we look at. We look at the tail area on both ends. It's a two-tailed test. However, if you had a directional hypothesis that your beta 1 is greater than 0, then you could just look at the tail of particular interest. Typically, people do these two-tailed tests because they are a little bit more conservative. You have to have a more extreme estimate in order to find significance. All right, so we'll stick with our alternative hypothesis that beta 1 is not equal to 0. Now, the problem is that we have this nice sampling distribution, and theory tells us that this sampling distribution will look nice and normal, but we need to take our B estimate and we need to turn it into some kind of standardized test statistic so that we can easily calculate what the p-value is. So knowing a B is equal to 2 it doesn't really help me. I need to be able to convert this into a standardized metric. And so what we do is we standardize the distribution, right? And so there's some standard deviation to this distribution, and we can standardize things. And so if you remember, how do you calculate a standard score or a z-statistic? You take the value minus the mean divided by the standard deviation. So in this case, we would take our sample value, B1, we would subtract the mean, in this case 0, and we would divide by the standard deviation of B1. And that would give us a z-statistic, and then we could look that up and see what the probability of that is. However, we don't know the standard deviation, right? We don't have access to that information, and so instead we have to estimate the standard error. We obtain an estimate of the standard error of B1, and now it's no longer a z-statistic, it's now a t-statistic. So we'll define our test statistic t to be B1 minus the null hypothesized value, almost always 0, so a lot of times you'll see people just leave that out. So the estimate divided by the standard error gives us our test statistic, t star, and t star is distributed according to a t-distribution with n minus p degrees of freedom, where n is the number of observations in the analysis, and p is the number of regression parameters. So in this case, p would be 2. We have 2 parameters, beta naught and beta 1, that we are estimating. And just keep in mind, sometimes reference books will use p as the number of predictors, so that would only be 1, and then you would see n minus p minus 1. So there are differences in terms of how p is used in these different texts. Here we use p as the number of parameters. All right, so now we have a distribution that is a t-distribution. All right, again, it's going to be centered at 0, and now we want to see, right, we convert our 2 into a t star, and so here's t star, and we look up and we see how extreme is a t star that big or bigger on either side of this t-distribution. We take the area under the curve on either side, we add it up, and that's our p-value. And ideally, we're hoping for a p-value that is less than 0.05. That's the typical threshold used to judge statistical significance. And so if a t-star statistic as extreme as the one we've observed would occur only less than 1 in 20 times, then we conclude that this null hypothesis is that it is an implausible value under the null hypothesis. Thus, we'll reject the null hypothesis, and instead we will say we have supported the alternative hypothesis. So that's the idea behind the t-statistic. Now let's do a little computer demonstration to see that, and then we'll return and talk more about the confidence interval.
All right, so here is some data that we're going to play with today, and what we're going to do in this demonstration is two things. First, I'm going to do just a simple analysis of this data to show what the t-tests look like and how you would interpret them, and then we're going to proceed to sort of flesh out the logic of the t-test by looking at how it's based on the notion of repeated sampling under the null hypothesis, and really show what that t-value is communicating for us. So here's some data. This is the same data we've looked at in some earlier demonstrations. Undergraduates who are randomly assigned a certain number of 8-ounce beers to consume, and then their road sobriety test performance was evaluated afterwards. That's our second sober variable. That'll be our outcome. Beers will be our predictor. We won't look at the other predictors here in this demonstration. That's the raw data. We can also look at the scatter plot to get a better sense of what's going on. And you see in the scatter plot the expected negative relationship that road sobriety test scores tend to go down with the number of beers consumed. But what we don't know yet is whether that's just within chance of zero, that in fact maybe there's no relationship whatsoever between these variables in the population, but just by luck of the draw we got 16 individuals into our sample where we see what appears to be a negative relationship. To evaluate that, we need to do our inference testing, and we saw the other day that we could use the analysis of variance table and the overall model F test to evaluate whether there is any significant variance explained by our predictor, and indeed we got a significant F test, so we conclude that indeed there is some relationship there. We also saw our model R square, 0.34, so we're explaining 34% of the variance in road sobriety test performance as a function of alcohol consumption. But what we're going to focus on right now are the parameter estimates, their standard errors, and the t-statistics that we obtained for those. So we see our B0 estimate is 9.6. In the absence of exposure to alcohol, road sobriety test performance is predicted to be 9.6. And then per additional beer consumed, here's our B1 estimate. We expect to see that road sobriety test performance will go down by 0.38 units. So a negative effect. And here are our standard errors. And remember, those standard errors are trying to capture the degree of sampling variability in those estimates. And so we then divide the parameter estimate by its corresponding standard error to get the t-statistic. So for B1, we take negative 0.38 divided by 0.14, we get negative 0.27. And then under the null hypothesis, that t-statistic, that t-star statistic is we can reference that to a t-distribution with n minus p degrees of freedom to see how extreme that is. And so we have 16 observations, that's n. We have 2 parameter estimates, that's p. We have 14 degrees of freedom. You can also look at the degrees of freedom for your mean squared error term, and that'll tell you the degrees of freedom for the t-distribution. And so we see that on a t-distribution with 14 degrees of freedom, a t-statistic of 2.71 or greater, either on the positive or negative end, is very unlikely. We get a p-value of 0.0168. So if the null hypothesis were true, obtaining a slope estimate of negative 0.38 would be very unlikely. We conclude it is implausible, and we therefore reject the null hypothesis and say that, well, probably in fact there is some effect in the population. It's probably not literally zero. All right, so that's how we would interpret the t-test in a single set of data. And in practice, that's really all you get is one sample. But to help flesh out the logic of the t-test, I want to show you what things would look like if we had multiple samples and the null hypothesis were really true. So I'm going to generate some fake data where the null hypothesis is true. This is a fantasy world where drinking beer does not affect your psychomotor functioning at all. And so there's no effect in the population, but we're going to generate data and see what we see in individual samples. So here's sample 1. So we have 16 individuals again, and you can see we have variation in number of beers consumed and variation in road sobriety test performance scores. We can see that in sample 2. We have a new sample of 16 individuals. They have different scores for beers and road sobriety test scores, but coming from the same population. sample 3, again, variation there. And so each sample has a new set of individuals with a new set of values, and we'll run a regression in each of our 3 samples. I'm going to scroll up to sample number 1 here. So in sample number 1, here's our true regression line is the dashed line, and that's a line with 0 slope. There's no effective beer on road sobriety test scores. In the sample, we get a slight negative slope, but it's tracking pretty close to the true line. In sample 2, right, in sample 2, we get a fairly pronounced negative slope. The slope is negative 0.3. Bear in mind that the true slope is 0, but just luck of the draw, we happen to get a sample where that slope came out negative. Sample number 3, the slope came out a little bit positive, 0.28. All right, so you can see that there is, at an n of 16, a fair amount of sampling variability in the magnitude of the estimated slope, even though the population parameter value, beta 1, is in fact 0. So the logic of the t-test is to say how much variability would there be when there is really no effect. We can do this for more than 3 samples. Here's 100. We can do this for as many samples as we want. I'm going to do it for 5,000 just to get a sense of what's going on, but I'm not going to print it out for all 5,000, of course. And so across all these different samples, I'm only printed out for 10 samples, we're going to get different estimates of B0 and B1. Right? So for sample 1, B1 is negative 0.04. For sample 2, B1 is negative 0.3, roughly. For sample 3, it's 0.28. All right, so for each sample, we're going to get a different B1. We also get a different B0, but I'm focusing on B1 because that's typically of more interest. And we can plot that out across samples. Now remember, I've only shown you 10, but I did 5,000. And so here's my plot across 5,000 samples. And you can get a pretty good sense of the sampling distribution of B1. Right? And then here, this little line here indicates where our particular sample came out. Right? So when we ran our analysis on the actual data, we got a slope of negative 0.38. So if the slope was truly 0, right, the center of this distribution is at 0, beta 1 is 0, then that's a pretty unlikely value. Very few of these B1 estimates come out to be more extreme than negative 0.38. Right? And so that's the logic behind the t-test, is we presume the null hypothesis to be true, we get a sense of the sampling distribution, and then we look to see how extreme is our particular estimate. Now in practice, we don't have the ability to sample over and over and over again from our population, but fortunately we don't need to do that. Is under certain assumptions, we know that this sampling distribution is going to be a t-distribution with n minus p degrees of freedom, and we can therefore calculate this p-value analytically rather than by having to do any kind of resampling approach. So that's the idea, and hopefully that gives you a better sense of what the logic behind that t-test really is.
All right, so that was the t-test, and the t-test, remember, is testing the null hypothesis that the beta is equal to 0. Right? Now that's useful in the sense that we can evaluate whether there's a relationship at all in the population, but it's somewhat unsatisfying in a few ways. Right? So how so? Well, one is that chances are beta 1 is not exactly equal to 0 in the population. It might be trivially small, but it's probably not going to be exactly 0. Right? In most of the things that we look at, everything's related to everything at least just a little bit. And so in some ways that's sort of a straw man that we're batting down with our null hypothesis, and really maybe what we're observing if we get a significant t-test is simply that we had enough power to reject it, right? But that, you know, it would almost necessarily be untrue, and we're really only evaluating if our sample is large enough to prove that. Another thing that's sort of unsatisfying about this t-test is that, let's say we do reject it. What does that really tell us? All it really tells us is that this effect is probably not 0, right? That our sample effect size is implausible if the effect is really 0. But, you know, all right, so we reject that null hypothesis. We say we're supporting the alternative hypothesis that it's non-zero, but what is it? Well, all we've really said is that it's not 0. So it doesn't give us a very good idea of what beta 1 actually is in the population. And so for those and other reasons, a lot of people have turned to using confidence intervals for their interpretation. Confidence intervals have a number of advantages. Right? They give us a sense of the overall precision of the estimate. They give us an interval that is sort of a plausible range of possible values for beta 1. And they can be used for null hypothesis testing. And so if the confidence interval excludes 0, then you would have a significant test. And if it includes 0, then you would have a non-significant t-test. And so it provides in some ways the same information as the null hypothesis test, but additional information that may be more valuable. Like the t-test, the confidence interval is based on the idea that we could sample from the population over and over again and obtain a sampling distribution of values for our estimated slopes around the true slope. Right? So let's say we have a true slope beta 1. Right? So the true value is beta 1, and we take samples around from the population. And in each sample we get a B1. And across all of the samples, we would get a distribution of B1s that would look something like this. Right, the average B1 would be the true population slope, but there would be sampling variability. Some samples would have a little bit higher estimate, some samples would have a little bit lower estimate. And so we want to understand that sampling variability. And we would expect that about 95% of these B1s would fall within plus or minus 2 standard deviations, right? So plus or minus 2 standard deviations of this sampling distribution should include, so 95% of those B1s should be within that plus or minus 2 interval. Now, you can flip that around. You can say, all right, so if 95% of the estimates are within 2 standard deviations of beta, then 95% of the time, if we took an estimate and we extended plus or minus 2 standard deviations from it, that interval would include beta. All right, so we could take a particular estimate. Let's say that estimate is right here. All right, so there's our estimate. And we go plus or minus 2 standard deviations. And 95% of the time, if we make an interval like that, it's going to include beta 1. And so that's the idea behind the confidence interval, is that we take our estimate, we extend by our margin of error, plus or minus 2 standard deviations, and 95% of the time, that should include the actual beta 1. So 95% of intervals constructed like that will contain beta 1. Any given interval might contain it, might not, but 95% of the time it will include that population parameter value. All right, so here's the trick. We don't know the standard deviation. So again, we can't, we don't know that, so we've got to be able to estimate that, and we have to adjust for it. Instead of using the normal curve, we use a t critical value. So instead of going plus or minus, the normal curve, it would be 1.96 standard deviations, to be a little bit more exact. Instead of going plus or minus 1.96, instead we use the t critical value. So we take our estimate, our B1, so there's our B1 for this particular sample. We take our estimate and we go plus or minus the t critical value at your alpha level, right? So usually that's 0.05, that's your type 1 error rate, coverage level that you want. And then n minus p degrees of freedom. All right, so we get our t critical value at our 0.05 alpha level with n minus p degrees of freedom, and we multiply that by the estimated standard error of beta 1. So this is our margin of error, and that gives us our confidence interval. So the confidence interval will have a lower bound and it'll have an upper bound. Any given confidence interval will either contain the population parameter of interest or not, but 95% of the time, our confidence intervals will contain those values, and we feel like that's pretty good odds. And so odds are this particular interval will be one of the ones that includes that population parameter. And so we use our confidence interval to get an idea of what a plausible range of possible values is for where that population parameter might be. And again, if that confidence interval excludes 0, then we would reject the null hypothesis were we to do a standard t-test. If it includes 0, then we would not reject the null hypothesis. But the advantage is we can see how wide is that interval, how precise is our estimate, and we can also see what possible values are within that interval are plausible. All right, so let's take a look at that
now. Okay, so you can see we're back to our beer data again. And I'm going to run our regression model one more time just to refresh our memory of the results. And this time I've augmented the output with the confidence intervals. So here are our 95% confidence limits. We obtained confidence limits both for B0 and for B1, but our primary interest would be the confidence interval around B1. And so we can see our 95% confidence interval runs from -0.68 to -0.08, right? And so because that confidence interval is entirely in negative territory, we would expect to reject the null hypothesis of 0, and you can see, sure enough, our p-value is less than 0.05. But in addition to providing us with that same information as the null hypothesis test, it also shows us a plausible range of possible values for what that population effect might be, what that beta 1 might be. All right, so again, to get a sense of the logic behind the confidence interval, we're going to do a little repeated sampling experiment using artificial data. I'm going to generate some data from a population in which the true intercept is 9, beta naught is 9, and the true slope is -0.4. And so the actual regression line in the population looks like this. Now, if the true population regression line looks like this, then we would still expect to see sampling variability around that line. Any given sample is going to give us a different estimated regression line. And so we can look at that for a few samples. So here's replication 1, sample 1. You can see the estimated regression line, the solid line, is fairly close to the true regression line, the dashed line. In sample 2, however, the estimated regression line is more negative than the true regression line. In sample 3, it's a little less negative than the true regression line. And we could do our repeated sampling experiment over and over again. We could collect, let's say, 100 different samples from this population and estimate the regression model in each of those 100 different samples, and we would get an entire collection of regression lines. And so you can see there's quite a bit of variability in the slopes of those regression lines at an n of 16. Now, what we're going to do next is see what our confidence intervals are going to tell us, right? And so I'm going to just plot out for each of our, we'll just take 50 of these regressions. I'm going to plot out where that confidence interval is relative to the true value. And so remember, our actual slope is -0.4. Every sample that we take from the population is going to provide us with an estimate and then a confidence interval. So the estimate would be in the middle of each of these intervals, and then the lower bound is on the left, the upper bound is on the right. So this is our confidence interval for sample 50, for sample 49, for sample 48, and so on. And you can see that a few samples do not, in fact, include the true population value. So this sample, our second sample, and we saw that a moment ago, had a steeper, more steeply decreasing slope, and the confidence interval for that sample, in fact, does not include -0.4. However, 95% of the samples, when we calculate that confidence interval, will include the true value of -0.4. So this one might not, and that one certainly doesn't. But 95% of the time, when we calculate that confidence interval as our estimate plus or minus the critical t value times the standard error, then we're going to obtain a confidence interval that will include that true population value. And indeed, we can look at that and see whether or not in our little artificial sampling experiment that was true. And so we can see I actually generated 5,000 samples of data, and 94.88% of those 5,000 had a confidence interval that included the true population value of -0.4, whereas 5% did not. All right, so that's the idea behind the confidence interval. It's based on this idea of repeated sampling. Of course, we only have one sample that we're analyzing, but we could imagine the ability to take multiple samples from the population and calculate confidence intervals on those multiple samples, and 95% of the time the confidence interval would include the true value. So let's go back to our model results. We obtained an estimate of -0.38 and a confidence interval from -0.68 to -0.08. 95% of the time when we calculate a confidence interval like this, it will include the true population values, so that gives us a sense of the plausible range population values for this effect. But it's always possible that this is one of those 5 in 100, 1 in 20, for which the confidence interval does not actually include the population effect. So that is our interpretation of the confidence interval. Is 95% of the time it will include the population value, but we don't know if this particular interval is one of those 95% or not. We bank on it. We figure 95% is pretty good odds, but we have no way of knowing in any given sample whether we have a particularly unusual sample or not. And so that's the idea behind the confidence interval, and it's a nice complement to the null hypothesis test. Some would say it should be used instead of the null hypothesis test because it provides additional information. But that's how you would calculate it and how you would interpret it.
Okay, so I hope that demonstration helped to make the confidence intervals a little bit more concrete to understand. So this sort of rounds out our discussion of inference in the regression models. We've talked about the overall model F test in the last episode. That's a test of whether your model as a whole is explaining variance in the outcome above and beyond what you might expect by chance. And then today we've talked about t-tests and confidence intervals for the individual regression coefficients. We've focused on the slope estimates and whether those suggest significant effects or not. But you can also do them on intercepts. They're just a bit less interesting there. These tests are going to get more interesting as we move into multiple predictor models. In the multiple predictor models, the overall model F test will test all predictors simultaneously, whereas the t-test will be for the unique effects of each individual predictor on its own. And so that's where we're going to turn in our next episode, is looking at multiple regression with multiple predictors in the model. Thanks very much for your time.